Good afternoon, everyone. Today we'll present our project on the design implementation of a digital dice simulator with an adjustable timer and irregular counter. Here's my group member. Here's our table of contents. Objective to develop a functional digital die simulation circuit using a JK flip-flop and 555 timer to design a 3-bit synchronous counter capable of irregular counting to cycle number from 1 to 6 to incorporate a user control time delay mechanism for precise clock signal triggering to ensuring circuit reliability through effective voltage regulation and noise reduction to analyze the system limitation for future optimization and enhancement. Introduction. As you already know that our primary objective was to replicate the randomness of physical dice roll using electronics. We designed a 3-bit synchronous counter with JK flip-flop to generate number from 1 to 6, paired with 555 timer for adjustable time delays. The user can trigger the dice roll with a button and the results are displayed on a 7-segment display. Literature review. Through our literature review, we identify gaps in existing designs such as limited automation, bulky structures, and signal noise. Our project addressed these issues by introducing user adjustable delays, improved voltage regulations, and feature enhancements like CMOS components. Thank you for your attention. My next team member, Manul Islam, will discuss from the next slide.
Assalamu alaikum. This is Manuel Islam. I will be explaining the working method of this project. Our digital dice simulator operates through an innovative combination of digital and analog components. At its core, we used a 3-bit synchronous irregular counter to emulate realistic dice randomness. When a user presses the button, it triggers a monostable timer featuring an adjustable time delay. The system generates a clock signal at 22 Hz through an stable timer which drives our counter to cycle through number 1 to 6. Um, then these are the key components that we used in our project: 3-bit synchronous counter and get or get and a timer, um, PMOSFET voltage regulator, and a BCD to 7-segment decoder. So then I will jump onto the methodology. The methodology involves careful integration of these components with the NE35N operating in both stable and monostable modes to handle timing functions. The counter output is efficiently decoded using the 74HC47 to display the final result on a common anode 7-segment display. So then this is the next state table that we got. This is all from my side. Thank you.
Assalamu alaikum. I am Hassan Habib. Today I am going to discuss about description of work experimental setup. Here you can see I have used a voltage regulator circuit 555 timer stable and monostable both synchronous counter using JK flip-flop. Stable used for clock pulse, monostable used for trigger to play dice game with switch. Both timer output connected to AND gate because when both true 1 to 6 synchronous counter will run and that will decode with decoder IC, and after that will show on 7-segment display. And this is our physical implementation. I am going to run this video. See, you can see in 7-segment display and also the binary number using LED. And here you can see this is our simulation, whichever you already saw in the experimental setup. And here is the simulation using multisim. From the next slide, my group mate Israt Jahan will continue. Thank you.
Assalamu alaikum everyone, I'm Mr. Jahan. So the simulation shows us the number from 1 to 6 in a random sequence, which is emulating the behavior of actual traditional dice. Key features are included as adjustable timer to control the ruling speed and irregular counter to introduce the unpredictable outcomes. Next slide, we know that the time delay T is equal to 1.1 into RC, where R as a resistance is equal to 10 ohm and the capacitor is 330. The graph shows us the monostable is always a low mode, which we need to change in high mode. We need to press the trigger button, which is connected to the 555 timer. The more increase of register value, the pulse will be increased eventually. The next slide here is a simple equation for a stable mode where high time is equal to 22.88 and low time is equal to 22.87 and total is 45.75. The frequency is 21.81 hertz and duty cycle is 50%. 7 LEDs were arranged to a pattern to represent the face of dice by activating the specific combination of LEDs based on the counter's output. The adjustable timer around the users. It allows users to modify the rolling speed and the irregular counter, introducing a satisfactory level of randomness. The LED display effectively represented each dice face, proving a clear and visual output. Thank you.
Hello, myself Redon Islam Sadiq, and here is my conclusion part. Successfully implemented a digital die simulator using 3-bit irregular counter timer circuits and a second and 7-segment display. Demonstrated alignment between theoretical calculations and experimental results, ensuring reliability. Integrated a stable power supply with voltage regulation and reverse polarity protection, highlighted the educational potential of combining digital and analog techniques. Limitations include the absence of precise testing tools and susceptibility of TTL components to damage. Future work transitions to CMOS-based components for improved cost, efficiency, and robustness. Incorporate automated dice rolling with variable timing for enhanced interactivity. Integrated advanced testing tools like oscilloscopes for precise calibration. Expand functionality to include multiple dice and game logic integration, optimize power consumptions, and improve durability for long-term usability. Here are the references, and thank you everyone.